I'm going to talk about this Katz-Klemm-Vafa formula, or was conjecture. I'm going to talk about the proof, which is joint work with Rahul Pandharipande. So briefly, the plan of the talk is I'm going to review quickly Gromov-Witten theory and what makes it so hard, which are multiple covers and things called degenerate contributions. And then I'm going to explain the conjectural BPS reformulation, so this is some kind of calculus for rewriting the numbers in a better way due to Gopakumar-Vara, and that'll be used to express this KKV conjecture in a manageable way. And then I'll describe all of this for K3 surfaces and K3 fibrations over curves, so threefolds, and state the KKV conjecture. And then to prove it, we're going to use a completely different curve counting theory, which is called stable pairs theory, so I'll review that. And then the way we're going to compute is using degeneration, so degenerating threefolds in particular into simpler pieces. And that's a very complicated part of curve counting theory, how this exactly works. So this is a theory developed by Jun Li, and it's really quite difficult to explain, but I'm going to try. So if I lose you at this point, you can maybe go to sleep here and then wake up here. So then I'll explain the Malik-Nekrasov-Akunkov-Pandharipande conjecture, and that relates two ways of counting curves. I'm going to state sort of the modern version of this, which relates stable pairs theory to Gromov-Witten theory. And that's been proved in some cases by Pandharipande-Pixton. We're going to use that. Plus, then, we're going to use this degeneration theory to prove something called a stable pairs Noether-Lefschetz correspondence, which I'll explain. And from that, we'll be able to deduce a different form of the MNOP conjecture, so one that's sort of local, so it's for a K3 surface inside its twistor space, more or less, or some part of it. And that is what we'll need to be able to reduce this KKV conjecture down to calculating stable pairs after some further degeneration on a rather simple space, so K3 times the complex numbers. Okay, so everything here is sort of a three-dimensional theory, even though I keep saying K3 surface. And so then one has to compute this stable pairs theory over here, but this looks just as hard as the Gromov-Witten theory, but I'll explain why certain things are better over here, and one can do the computations, and why certain miracles occur. Okay, so briefly some history. So Gromov-Witten theory is very difficult. So for instance, you get 2 Fields medals for computing the Gromov-Witten theory of a point. So that's how to do curves in a point. Then in genus 0, which is a better behaved theory, it's what's called enumerative. I'll say something about it later on. Kontsevich calculated the Gromov-Witten theory of P2, and the full Gromov-Witten theory of a curve in all genus was computed finally by Akunkov-Pandharipande in 2003. So we understand about counting curves in curves. And that's about the limit. Unless your space has a lot of symmetry, it's a toric variety or something, that's really all that's known in Gromov-Witten theory, at least in full Gromov-Witten theory in all genus. We know something about surfaces, especially Tabbs' results. Also the gotcha conjecture, which builds on the Yau-Zaslow conjecture, which is on the next slide about K3 surfaces. But we're going to jump straight to threefolds, where there's the MNOP conjecture. And this relates Gromov-Witten theory to another curve counting theory, so that doesn't really sound like progress. But the idea of this talk is to give the impression that this other theory is slightly better behaved. And this MNOP conjecture is really useful. So this is the first time it's been really used to try and compute the full Gromov-Witten theory of a space of dimension bigger than 1. Okay, so the MNOP conjecture was proved for toric varieties by MOOP. So this first O here is a Blomkopf. So you can imagine with toric varieties you have a lot of symmetries and localization, so you can reduce it to a combinatorial problem. But it's much harder than that, and it's solved really using geometry. And then, spectacularly, it was proved for most Calabi-Yau threefolds by Pandharipande and Pixton a couple of years ago. So those Calabi-Yau threefolds that can essentially be degenerated to toric varieties. So they proved a souped-up version of the MNOP conjecture for toric varieties, so MOOP plus epsilon or 1 over epsilon or something. And then their better MNOP conjecture contained the MNOP conjecture for the toric varieties, plus how you put it all back together again to produce your variety which has been degenerated into a union of toric varieties all glued together. Okay, so we're going to use this to convert the Gromov-Witten theory problem to a problem in something called stable pairs. So it's a more linear theory in some sense. It's a sheaf theory. Okay, so K3 surfaces, the history is that in genus 0, there was the Yau-Zaslow conjecture in 1995 for precisely what the Gromov-Witten theory looked like, which was proved in primitive cases by Beauville and Bryan and Lung, and then in all classes by Clem, Malik, Pandharipande, and Scheidegger in 2008 by mirror symmetry for hypersurfaces and toric varieties, so by translating the problem using mirror symmetry into a problem in calculating periods. And then the full Gromov-Witten theory of K3 and K3 fibered threefolds was conjecturally described. So despite the fact that mathematicians can't do anything more than curves, remarkably, back in 1999, Katz-Klemm-Vafa were able to predict the entire Gromov-Witten theory of K3 and K3 fibrations. And their prediction is in terms of modular forms. So I'll say something about it later. You really only have to compute a few cases, and then everything else falls out. All the other Gromov-Witten invariants follow. And this was proved in primitive classes a few years ago, again using the MNOP conjecture for toric varieties and doing the degeneration. But today I'm going to talk about general classes. So this is getting to the heart of the problem in Gromov-Witten theory. So all the multiple covers and all the degenerate contributions. So the general case. Right, so this is Gromov-Witten theory in one slide. So I'm not doing symplectic geometry, just I'll restrict to complex projective varieties. I have a degree or a curve class, and I'm going to count curves in that class. I have a moduli space of stable maps, so Gromov-Witten theory counts stable maps. So these are algebraic or holomorphic maps from a curve to X, where the curve is almost smooth, at worst has nodal singularities. And there's the stability condition that the automorphisms of the curve, which fix the map, have to be finite. So I'll give some examples in a minute. And so the moduli space is what's called a Deligne-Mumford stack, so that means it's some kind of singular algebraic object modeled on a scheme, but also with orbifold behavior, so modeled on a scheme modulo a finite group. And so it's singular, its deformation space keeps jumping around. Its deformations, you don't know what the dimension of the deformation space is, because it changes. But the deformations minus there's a natural obstruction space, the difference in dimension of these two is always a topological constant called the virtual dimension, given by this number. So in particular, for a threefold, this goes, and for a Calabi-Yau threefold, this goes, and the virtual dimension is always 0. So you should just count curves in the Calabi-Yau threefold case. And this phenomenon of deformations minus obstructions having constant dimension more or less is the same thing as meaning that there's something called a virtual moduli cycle. So even though the space has the wrong dimension, it always has possibly too high a dimension. There's a cycle in there which plays the role of the fundamental cycle, and it has the correct dimension. So it's in the Chow group or homology of dimension, this dimension here. So there's a cycle there which is the right thing, even if the moduli space has the wrong dimension. There's a cycle there which is good enough, and you integrate cohomology classes over it, which amount to imposing incidence conditions on your curves, insisting they go through points or various cycles and so forth. And that gives you Gromov-Witten invariants. And they're rational numbers because of this, these automorphisms up here. Okay, so if a curve is a double cover, then it has a Z mod 2 of automorphisms, and it only counts as a half, not as 1. All right, so then I just wanted to illustrate, this seems rather arbitrary maybe if you haven't seen it before. I just wanted to illustrate what these conditions are about. They're about making this space compact. So in particular, families of stable maps have to have limits. So these are just some trivial pictures of what the limits can be. Okay, so the first one is for conics. So I take some conics, x squared equals ty, and I tend t equal to 0. So I end up with a doubled line, a fattened line. That it cannot be the limit in Gromov-Witten theory of these curves because it is not a stable curve. It's not smooth except for nodes. So what the limit actually is you take the natural identity maps here from this curve to this curve, so the natural embedding of P1 as a conic here. And in the limit what you find is you get a double cover. P1 double covers this line, the thin line x equals 0 there. And that's the limit of stable maps of these curves. Okay, and that's a double cover. It has a Z mod 2 of deck transformation automorphisms, and so it counts as a half. So that's the Gromov-Witten limit, is this guy here. And in stable pairs later on, the sheaf theory, the limit will be this guy. It will be the thickened curve, the scheme theoretically thickened curve. So the compactification will be different for stable pairs, but for Gromov-Witten theory, this is it. So this is the simplest example where you get rational numbers counting your curves. And then here's a case where I'm going to give it, the example is over on the right-hand side here, where you have a family of smooth elliptic curves degenerating to a rational cuspidal curve. So this is the, this curve appeared this morning as in Camillo's talk as this was this was the bad guy. So one way of producing it is the following. Just take a smooth family of elliptic curves, like just a product family or something, blow up one point, so you get the same family of smooth elliptic curves but with a P1 attached, and now blow down this elliptic curve here. And you end up with this picture here. So you end up with elliptic curves degenerating to a P1 but with a singular point. So when you blow down this curve, you also blow down an infinitesimal direction up the P1. You squash that as well, and you get this cusp singularity here. Okay, so in Gromov-Witten land, that is not allowed to be the limit of these smooth curves, because again, it has a worse singularity than a node. So what is the limit? Well, it's drawn up here. It's how we produced it. So the limit has to be this curve, where this curve just has a node, so it locally looks like xy equals 0. So the limit of these smooth curves is not this cuspidal curve, it's this nodal curve mapping and contracting an entire component plus an infinitesimal direction down to a single point. And you can imagine this could also lead to rational numbers. There can be automorphisms of this elliptic curve fixing that point. And so you can get rational numbers here. And worse, you're now going to have to glue on. You can imagine, if you look at this limiting map to this curve, if you forget about everything else, you just look at this curve with a cusp here, and you look at this map from an elliptic curve plus P1 to it, I can now just change this elliptic curve. I can deform this in the moduli space of elliptic curves with one point, and map all of that, glue any one of those elliptic curves to a P1 in the same way, and then just map it to this cuspidal curve here, just by contracting it. And all of those guys are stable maps as well. So all of those live in this so-called compactification. This compactification of this space of curves is much bigger than the original space of curves. And you have to, in Gromov-Witten theory, you have to integrate over all such objects. And those are called degenerate contributions. So the simplest example is if you take a rigid P1 in a Calabi-Yau threefold, so a -1, curve in a Calabi-Yau threefold. That contributes, as you would expect in genus 0, to Gromov-Witten theory as one curve. It then contributes by its multiple covers in genus 0 by something called the Aspinwall-Morrison formula. So degree D multiple covers contribute 1 over D cubed. But then much worse, it contributes in higher genus. So if you have any genus G curve, you can just glue it abstractly to a P1, and then map it to the P1 in the Calabi-Yau threefold by contracting your genus G curve. And you have to integrate over the families of all such genus G curves. So these are called degenerate contributions, and they're all there in Gromov-Witten theory as well. And this is why Gromov-Witten theory is a mess and is not enumerative. It's not just counting what the Italians used to count in algebraic geometry. And they're the things that make Gromov-Witten theory hard, and they're the things that we have to compute. But in all those examples that I mentioned, you could see there was an underlying integer. So here, underlying this half, this stable map here, which counted as a half, there was an underlying 1, which was in half the homology class. So we're in the homology class of 2 times the hyperplane section here. If we go to half of that, so 1 times the hyperplane section, there's a line there, x equals 0, and it was being double covered. And that x equals 0 counts as 1 in Gromov-Witten theory. So there's an underlying integer. And in all those degenerate contributions I was discussing, mapping to a rigid curve in a Calabi-Yau threefold, there were all those dreadful integrals over the moduli space of genus G curves. But underlying them all, there was an integer, just 1, counting that rigid genus 0 curve. And conjecturally, something much more general happens, which is that there are, just in the same way, there are integers underlying all of Gromov-Witten theory. And this is they're so-called BPS numbers. So this is the theory of Gopakumar-Vara. They have a way of defining these numbers which mathematicians have never made rigorous. So I'm not going to discuss that. I'm just going to use their formula. So this is their formula. So they define some integers, and they give a formula for how the rational Gromov-Witten invariants are written in terms of them. Okay, so, but the point of view today is you can define these integers in terms of these rational numbers, or these rational numbers in terms of these integers. This is an invertible transformation. So we're just going to use this formula to define these numbers here. It's not then clear that they're integers, I beg your pardon, but the conjecture is that they're then integers. So what we're going to do is we're going to repackage the Gromov-Witten theory via a universal transformation written here, which you're not really supposed to understand. And in terms of different numbers here. And then the Gopakumar-Vara conjecture would be that these numbers are integers. I give you an example. If your class is irreducible, so your curves can never be sums of other curves, then then you're dealing with just d equals 1 here, and to leading order sine u over 2 is just u, and this becomes the same as this. So what happens is that the BPS number is the same as the Gromov-Witten invariant, which is an integer. Okay? But then if I go to 2 times an irreducible class, what this formula gives is it gives you the Aspinwall-Morrison multiple cover formula. So what you find in genus 0 is that the Gromov-Witten theory in 2 times this irreducible class is what you would expect from the Aspinwall-Morrison formula. So you expect all your classes, all your curves in half the class to contribute as 1 over 2 cubed by double covers. So all the curves here in class beta get double covered and contribute 1 over 2 cubed to this number. And then what's left is all the curves which aren't multiple covers, which are irreducible. And that's what the BPS number counts. All right? So you might think of the BPS number as counting irreducible, reduced, nice curves in X. Those, of course, don't form a compact moduli space, and no one knows how to make sense of that. And it really isn't quite true in higher genus either, but it's useful to think of it that way. So you should think of these as roughly counting irreducible, reduced curves. And as I say, conjecturally, they're integers. All right, so what you should just take from this slide is there's a way of rewriting these numbers in by some universal formulae. So that was Gromov-Witten theory. Any questions? So now I'm going to talk about K3 surfaces. So if you go back to that formula for the virtual dimension, you find for a K3 surface, genus G curves live in a moduli space of virtual dimension G minus 1. So it's well known that curves of genus G move in G-dimensional moduli spaces on K3 surfaces. But their virtual dimension is not G, it's G minus 1. And the reason is there's always an obstruction space. And there has to be, because as you deform the K3 surface, you can lose all those curves. Because you can deform the K3 surface so that your curve class no longer has Hodge type 1,1. It picks up some 0,2 part. And so, indeed, because of that, the Gromov-Witten invariants of K3 surfaces all have to be 0. Because if I deform the K3 surface so that the class isn't algebraic, then of course there are no curves. All right, but that's not the KKV conjecture. So we're going to modify these aren't the Gromov-Witten invariants that I'm going to talk about. So the reason is the obstruction theory contains this trivial one-dimensional piece when you work it out, and it's just the 0-tooth part of the cohomology of the K3 surface. It's just the dual of the holomorphic 2 form. And that's the piece which sees whether or not your homology class has any non-1,1 Hodge part. And so this gives you two ways of seeing the Gromov-Witten invariance as 0. Either you deform the K3 surface so that there are no curves, or you see that the obstruction theory contains a trivial vector bundle, line bundle, and so its Euler class is 0, and so you see that the virtual cycle must vanish. All right? So we don't want to do that. What we want to do is we want to remove that, and you're allowed to remove that. I mean, of course, that would mess up your obstruction theory, but so long as you promise never to move your K3 surface to violate so that this happens. So if you work with only K3 surfaces such that your curve class, which you've fixed, remains of type 1,1, then you'll never touch this obstruction theory here, and you can just remove it, and you'll still have a perfectly good obstruction theory. So what you find is you can remove it, you can do the deformation theory necessary, and you get a new theory called reduced Gromov-Witten theory, which has virtual dimension 1 higher, genus G. All right? So you should think of, so let's take G equals 1, you would have a K3 surface which was elliptically fibered. Then indeed those elliptic curves move in a one-dimensional family. Some of them will be nodal, then you'll get some immersed P1s, and those indeed are rigid, they're moving in a zero-dimensional family, and they have genus 0. So that's all in keeping with this. And what was going on up here was that I could deform that K3 surface so it was no longer elliptically fibered, because the class would no longer be of type 1,1. And that was why that was there. Okay, so you can do that so long as you stay inside this so-called Noether-Lefschetz locus. So this is the locus of K3 surfaces where this class beta has type 1,1. And what I've written there doesn't quite make sense. I'm being very vague. You have to mark the K3 surface and so forth, but it'll do. All right? And this locus is a divisor because it's the locus where your class beta, its integral against the symplectic form, the 2,0 form, is 0. So there's one equation cutting it out. All right? So long as you stick to these divisors, you can define these invariants. Now, the point is, of course, because it's a codimension 1, this divisor, you can always move off it, and that's why we had this problem here. But if you slice it with something one-dimensional, because it's codimension 1, then you can't move off it. So that's the other point of view, is the three-dimensional point of view. This is a picture of the moduli space of K3 surfaces. This is this divisor, the Noether-Lefschetz locus, codimension 1. And what you can do is you can cut that with something of dimension 1, which looks remarkably similar to codimension 1 in this picture. So that's some kind of disk or algebraic curve inside the moduli space of K3 surfaces. And now that guy isn't going to fall off the Noether-Lefschetz divisor if you start perturbing it. So what does that correspond to? Well, that's obviously just a threefold, a K3 fibered threefold, fibering over this disk. And so this is the other point of view on what these invariants are. Really, they're threefold invariants. What I'm interested in is this threefold, which is a K3 fibration, where what I've done is I've chosen this disk to be transverse to this Noether-Lefschetz divisor. So the curve class inside this K3 surface central fiber here does not deform to the other fibers. It's not of type 1,1 on the other fibers. So all the curves in that fiber class all lie on the central fiber. So the moduli space of curves in this threefold at least close to the origin, in this fiber class, beta, is the same as the moduli space of curves in the central fiber. So this is some kind of algebraic approximation to the twistor space of S. For the rest of this talk, you may as well think of this as the twistor space, at least over C rather than P1. Some kind of local version of it. Okay, but we have to use algebraic approximations because stable pairs theory is only defined within algebraic geometry. But more or less, that's what's going on here. Okay? So I'm really interested in the Gromov-Witten theory of these things. So as I said, the moduli, so T is for twistor. The moduli space of curves in the twistor space, they all lie in the central fiber. And so you find that this moduli space of stable maps, they're the same, but their obstruction theory is very different, as you would expect, because in particular, I had virtual dimension G minus 1 over here, but 0 here, because this is locally a Calabi-Yau threefold. So they have very different obstruction theories. And we're really concerned with what this whole talk is about. So this is still the introduction. These invariants, the Gromov-Witten invariants of this twistor threefold. And the reason I discussed all that reduced obstruction theory stuff was because it turns out, because when you compare these two obstruction theories, what you find, it's a very easy calculation, is that the Gromov-Witten theory of the threefold can be expressed entirely in terms of the surface, in terms of that reduced class that I introduced last time. And what is it? It's an integral over that reduced class of a certain G-dimensional cohomology class, because this is G-dimensional. And that G-dimensional cohomology class is a certain Hodge class. But you don't really... The only reason I went over all this was to show you that this invariant here only depended on the K3 surface. It's defined as a threefold invariant, but it only really so it's a three-dimensional Gromov-Witten invariant, but the only data that's important is a K3 surface. And this is the invariant I'm interested in. All right? So if I lost you, this is all that matters here. So this is the contribution of your K3 surface S to the Gromov-Witten theory of any K3 fibered threefold in which it appears as a fiber. So it's how it contributes to threefold Gromov-Witten theory. Yeah? No, that's right. So delta somewhere, hopefully, was transverse. Here we are. Delta was transverse to these Noether-Lefschetz divisors. There you go. Right, I see, yes. No, that's correct, yes. So it only contributes in this way so long as you have that transversality, yeah. And otherwise it contributes by a more complicated Noether-Lefschetz Gromov-Witten correspondence, which will come later. So I will make this statement more precise later on. Right, so we're getting close to the end of the introduction. So now, we've finally defined the objects of study, these Gromov-Witten invariants of these K3 surfaces. They're really threefold invariants, so it makes sense to write them in Gopakumar-Vara form in terms of this BPS integers. And then, a miracle is supposed to occur. So this is the KKV conjecture. The first thing is that these things, because they're deformation invariants, so long as you deform the K3 surface so that beta remains of type 1,1, by the Torelli theorem, they're really almost topological. They only depend on the only invariance you have of beta, its square and its divisibility. So they depend only on the square of beta and the divisibility of beta of this class, whether beta is 5 times another class or 2 times another class or primitive. And one of the amazing things about these BPS reformulations is that conjecturally, these things aren't just integers, but actually, they don't depend on the divisibility of beta. So this is incredible. So what this says is that whatever these Gopakumar-Vara invariants calculate, they don't see any multiple curves. So if you're trying to calculate the Gromov-Witten theory, well, the BPS numbers in some curve class, which is 2 times some other curve class, that's fine. You don't need to do that calculation because the answer you can just convert to a completely different curve class of the same square, but which is primitive. And the answer will be the same there. It's absolutely extraordinary. And it's because, more or less, curves in these two classes look the same, except the class which has divisibilities 2 has these extra curves, which are multiples, which are double covers. And the BPS invariants you're supposed to think of have already got rid of those. All right? So this is some kind of philosophically very appealing result. Okay, so that's the first thing. So because it only depends on beta squared, it only depends on this h, I'm going to rewrite them in terms of h and then give you a formula. So we denote this by ngh. And then this is the KKV formula. So when you set z equals 1 in this formula, then you're just counting genus 0 curves. You're just taking g equals 0, and you get the Yau-Zaslow formula. So that's where this 1 minus q to the n has power 24, and you get the discriminant modular form. All right, but really I'm going to concentrate on this. This is the important thing. Once you've got this, it becomes much easier to compute this, because you can work in a primitive class, which had already been worked out. Okay, so this is the key thing. So any questions? All right, so if you work out what this says, it says lots of things, but for instance, if the genus is bigger than h, it says that the BPS number is 0, so again, that's incredible. That says when your image curve has arithmetic genus h, BPS numbers do not count any maps from curves of higher genus to that curve. All right? So in particular, it is a smooth curve. The only maps to a smooth curve, the only holomorphic maps from a curve to a smooth curve of genus h all have genus bigger or equal h. And the BPS numbers only see the ones of the same genus h. They don't see any of higher genus. So that's saying that they don't count any degenerate contributions or multiple covers. And when g equals h, you get the sign, up to sign, you get the Euler characteristic of the linear system of curves of genus h. So you take all the embedded curves of genus h, actually embedded rather than crazy maps. They form a linear system of dimension h, and its Euler characteristic is this. And here's a table. So these are all zeros, and you see this is a table of numbers. All right, so the strategy is we're going to use degeneration to try and make everything simpler, make the geometry simpler. And by using this degeneration, we're going to split spaces up, and using that, we'll be able to form prove an MNOP conjecture which is local to this K3 surface. So actually, it's more or less, it's either on the K3 surface inside the twistor space or the K3 surface inside itself times C. And that will eventually reduce everything to a calculation of stable pairs on this threefold, where you can use localization in the C direction. And so what that will involve then, finally, is so we've turned that will turn the Gromov-Witten theory problem into a stable pairs computation. So that's some kind of sheaf theory problem. And, you know, to first order, they look just as hard as each other. So the multiple covers in Gromov-Witten theory get replaced by stable pairs, which instead of lying on S, are kind of thickened in the C direction scheme theoretically. Whereas in Gromov-Witten theory, they would have laid scheme theoretically on S. They would have just been multiple covers. Here they get fattened in this direction. But then certain advantages of stable pair theory, in particular something called its symmetric obstruction theory, which I'll explain, make computation on this side actually possible. So I'll explain that. And that gives a certain vanishing theorem, and then you can calculate. Okay, any questions? So now I'm going to launch into this degeneration theory. This is how you compute Gromov-Witten invariance and stable pair invariance. So this is kind of a bit miserable. Oh no, I'm not. Oh, there you go, good. Oh, this is much more pleasant. Okay, the misery is still to come. So I have to tell you what this other theory is that we're going to compute. with instead. So there's stable pair theory. So what's the stable pair? So at the moment, this only makes sense on algebraic varieties. So it's a sheaf, a one-dimensional sheaf, plus a section with the stability condition that the sheaf is pure and the section has zero-dimensional co-kernel. So if you don't care to know what any of that means, roughly speaking, it's a curve with some points on it on your algebraic variety. So the sheaf is supported in one dimension, so it's supported on a curve. This purity condition means it's really a curve. It doesn't have any embedded points or free points floating around. And then this section is generically an isomorphism from the structure sheaf of that curve to this sheaf here. So more or less, this F here is a trivial line bundle on the curve away from a few points. And then on those points, you get some co-kernel, and that gives you some points on your curve. So more or less, it's a curve in your variety plus some points. And if your variety is two-dimensional, this is really true. And if it's three-dimensional, it's a little more complicated, but this will do. All right, so it's a curve plus points. So for instance, you can take the trivial line bundle on the curve with the section 1, that's a stable pair, and what that corresponds to is the bare curve with no points. Or you could have a curve with the divisor on it, with that gives you a line bundle on the curve with a section vanishing on that divisor, and that's a curve with that divisor as the points. And then a case where you get a Weil divisor instead of Cartier divisor, if you care, is this. But anyway. And again, there's a compact moduli space. It's projective and it's a scheme. There's no orbifold behavior. There's no finite groups. So these are really embedded curves. There's no map. So there's no automorphisms. So that's an advantage. And again, there's a curve class beta, and now the genus gets replaced by this number n, which is the holomorphic Euler characteristic of the sheaf. But roughly what it is the genus of the curve is 1 minus the genus of the curve, then plus the number of those points on the curve. All right? So now, if you're in 2 dimensions, which I'm not, but if you're in, this will be useful later, if you're in 2 dimensions, then the genus of the curve is determined entirely by the adjunction formula from the class you're in. And what you find is that stable pairs on this surface are really the same thing as curves and points. So this is that statement. So this is the Hilbert scheme of curves in class beta in the surface. Over that, you have a universal curve, and you take n points on that universal curve. You take the relative Hilbert scheme. All right, so this is really true as schemes. But for threefolds, it is slightly more complicated. So this is an example. Here you have, for instance, in 3 dimensions, you have more space, basically. So you can have 2 branches of a curve coming together in 3 dimensions and gluing at one point. And that point will then kind of bubble off. So if these 2 branches in 3 space suddenly come together, you get a point pops off. And then in a separate family, you might smooth that curve, and the point might move off around the curve. All right? So this is an example where the genus has gone up by 1. You've gone from genus 0 to genus 1. But the number of free points has gone up by 1 as well. So this formula has remained constant. All right, so and this is the reason why you need the points. When those 2 branches came together and glued together, you lost a point. So you didn't have a flat family. So somehow you have to recover that point somehow. So in Gromov-Witten theory, the way you do that is the limit of these embedded curves here is the stable map, which is the normalization of this curve, where the 2 branches are really apart, and it maps to that curve by gluing those 2 points together. In stable pair theory, it's an embedded theory, there's no map, and the limit is really curve plus a point. All right, so this is why you need these points, and this is how they're related to the genus. Okay, so, but it's not so important. You should just think of it as some kind of theory which is, instead of using maps or parametrized curves, it uses sort of subschemes and unparametrized curves. And it has some deformation theory. That's not so important. And in 3 dimensions, this doesn't work in other dimensions. In 3 dimensions, the deformations minus obstructions, again, have a constant virtual dimension, the same one as before, because we're in 3 dimensions. And so we get a virtual cycle. And in particular, all we care about is the Calabi-Yau case, where, again, the virtual dimension is 0. And so we can count. We can just integrate 1. We can count the number of... Virtually, we only have a finite number of points, and we just count them. And that's the count of the number of curves in class beta in X. So this is a stable pair invariant. And it has the advantage that it's an integer. Okay. Okay, so now it gets miserable. So how do you compute either of these theories, Gromov-Witten theory or stable pair theory? I haven't related them by the MNOP conjecture yet. That'll come in a second. And the way you compute them is by degeneration. So what you do is you degenerate your variety into a union of two pieces. And now what you would like to say as well, curves on x should be the same thing as like a curve on x1 and a curve on x2, which meet in the middle. So along this divisor D, their boundary values, so the curve on x1 might intersect D in little d points, and the curve on x2 should intersect D in the same little d points. So you should end up with some kind of correspondence like this, where this is the space of little d points on big D. Okay, but to do this, that obviously doesn't work if the curve itself falls into D. So here's the picture of x degenerating into two pieces, x1 and x2, with D in the middle. And what we're trying to avoid is having a component of the curve, or the curve itself, lying in this crease in the middle, in D, because then this won't work. So what you do at that point is you blow up D and you end up with the curve in here instead. And then again, this curve here might wander off and fall into this crease here, but you don't want that, so then you would blow up again, and then you get another D times P1, and so on. I guess I'm drawing the case where D has trivial normal bundle in these xi's. Otherwise, this D times P1 would just be a P1 bundle. Okay, so Jun Li has set up a theory which does exactly this. So what it does is it replaces curves on x1, this naive thing which didn't quite work because of curves falling into the divisor, with things like this. So you replace x1 by either x1 or x1 with one of these bubbles joined on, or x1 with two of these bubbles joined on, and you take curves on that. And then I'm going to glue, and then I also take curves in x2, maybe with a bubble, and so forth, and then I'm going to glue the two together in a minute. So that's what's going to replace these pieces here. Okay? So I'm going to concentrate not on Gromov-Witten theory, but on stable pair theory. So there, Li and Wu did this. So there are moduli spaces of relative stable pairs, relative to this divisor D. So here's my space x1 with a divisor D. And what I have to do is I have to take curves in not only that, but that with any number of bubbles added. And each time I add a bubble, I add a whole bunch of I add a whole C star of automorphisms, acting by thingy on that P1. Squashing, I don't know. And in their relative theory, the curves are required never to have any components inside these creases. And therefore, they have a well-defined boundary value. You can talk about the number of points that they hit this final divisor D at. Okay, so that's what I needed in order to do this business here. So I can talk about the boundary of these curves and the boundary of these curves, and then I can glue them together. All right? So really, you're supposed to think of this as an Artin stack if you're sophisticated. But if, like me, you're not, then what this really is sort of curves on here, such that no component has fallen into a crease, and where you divide out by an equivalence relation that two curves are considered the same if they differ by one of these automorphisms. All right? So if I move this curve by C star to lie over here, that's just the same. And I only take curves with finite numbers of automorphisms. So that I'm not allowed to just add a bubble on which is completely empty, because then I'll have curves with a whole C star of automorphisms, and those won't be in the moduli space. All right, so because of this, I end up with certain moduli spaces, which are Deligne-Mumford stacks. With virtual cycles, you have to check the deformation theory works, but me and Daniel Huybrechts did that, and you end up really with a whole theory with virtual cycles, and you get the formula you want. You find that the virtual cycle on each piece, glued across the middle, is a specialization of the virtual cycles on all the smooth pieces. So the XTs were the smooth guys out here, which degenerated to these two pieces. So the whole theory works as you would expect. Okay? So, but just at the expense of, you're no longer computing pure curves in just one piece or the other. You have all these bubbles. All right, so how are we going to apply this? We're going to apply this to that twistor threefold. So we had a K3 surface sat inside this twistor threefold, and we do its deformation to the normal cone. So we stretch it around the central fiber, we stretch delta until the whole bubble pops off. And we're going to compute, instead of the curve theory over here, we're going to compute curve theory over here and get the same answer. And we're only in fiber classes, and curves are not allowed in this crease here. So actually, they must all lie in here. In T, the only curves were in the central fiber S. I guess I'm drawing it there now. And S, once I've degenerated, S is a crease, and I'm not allowed curves in there. So actually, the curves can't lie in T anymore. They have to lie in all the bubbles. They have to lie in here or one of the bubbles. Okay, so the curves are the red things, and they all have to lie in here. So you can see now we've reduced to a theory which depends only on S. I'm sat inside P1, all these bubbles, P1 times S, plus this final bubble where I'm not allowed to lie in the last fiber there, so it's really a C times S over here. Okay, so we degenerated the moduli space to one which depends only on S, and it's this so-called rubber moduli space. So we end up with stable pairs in this thing. S times C, that's this piece. Relative to the S at 0, that's this one. That's what allows all these bubbles to pop off. Because curves can't land in there. Each time they do, I produce a bubble. Divided by C star. There's a C star acting on here, so this is a stack. Okay? And this is actually a compact moduli space. Even though this is a non-compact space, the curves can't kind of fall into this C times infinity here because of the C star action. All right? So as I said, this is painful. Don't worry about it. This reduces everything to something which depends only on S, but with a very different deformation theory. When you work through the Jun Li deformation theory, you see that deformation theory depends on T, unfortunately. So you analyze this, you use an induction on the number of bubbles, and what you find is the following relation. It just pops out. The geometry just gives it to you. It's extraordinary. So it says that the generating function of stable pair invariance of that twistor threefold in a fiber class, when you take the log of it, which you should think of as replacing stable pair invariants that count disconnected curves, any old curves. When you take the log, that gives you connected curves. This new generating function has rational coefficients now, not integers, but that's okay. They're underlied by integers. So this turns out to be equal to the stable pair invariance of this crazy geometry here. But again, reduced. That means I took out the trivial piece of the obstruction theory. So it wasn't 0. Okay, so you get some crazy formula. Right? Oh, that's the end of the pain. So all I'm saying is, using this degeneration, stable pairs in that twistor threefold, which can leak out of the central fiber, scheme theoretically, so it looks like they depend on more than the K3 surface, actually can be written in terms of invariance just of the K3 surface. And in fact, invariants which are more or less made out of the K3 surface times C. So I've got rid of all the non-trivial infinitesimal information in the twistor space and just replaced everything by the trivial normal bundle. Okay, so that's some kind of progress. Anything else I wanted to say? Yeah, but it was just easier in the Gromov-Witten theory case, because in Gromov-Witten theory, everything lays scheme theoretically inside S. And here it doesn't. So you have to do this. But I did this for another reason, as you're about to see. Okay. Good question. Right, so I did that for the following reason. We also get, so I'm now going to make precise this idea that Yaim just mentioned, that I'm going to do stable pair theory now. The stable pair theory of any K3 fibered threefold should come from the stable pair theory of the twistor space, so these invariants here, in every time a K3 appears in the fibration with the right fiber class, which is algebraic, it's of type 1-1. So we're going to make that precise, and that's this pairs Noether-Lefschetz correspondence. Okay, so we can't do that for ordinary stable pairs because that counts disconnected curves. So it doesn't work. You get a curve which lies on two fibers at once, so that's not going to work. But with these connected curves, which are defined by this log formula here, so you take these connected invariants just formally by taking logs, we're going to prove a correspondence for these guys. Okay? So the way you do it is you do exactly the same technique. You degenerate, you take this guy, every time you see a fiber which can have curves in it, you deform it to its normal cone. So you bubble it off in the way I said before. So you just do the same thing just many times to many fibers across your X, and you get this formula. And I'm not going to go through all this. You can look in the paper. But roughly speaking, it's what you think it is. It says that curves in X are curves in S, these are the K3 invariants, times by the number of S's, the number of fibers, which have beta, a class beta of type 1,1. All right? Yes? Yeah, so this is a global, that's right, a global projective threefold. So the twistor space was the way we defined the local theory, and now this is a global X. And the reason I want a global X is because I want to use the MNOP conjecture. So that's another good question. Why should I do this? So I've motivated by this by just saying, well, this is what I meant by saying those invariants are the local contribution that you get in any K3 fibration. Well, here's any K3 fibration. And the reason I want to use any K3 fibration is because I want to use the MNOP conjecture. So this will be useful to us in a minute.
But you can't lie inside of the.
The way I've said it in this talk, yeah, but we prove the general case as well. Okay? So there's a similar Gromov-Witten Noether-Lefschetz correspondence, which goes back a lot longer, because this is slightly easier to handle because all the curves lie in S. There's no scheme theoretic popping out. Okay, so there's a similar correspondence for Gromov-Witten theory. Also, Gromov-Witten theory is a connected theory, so that it handles it better. And we're going to apply both to an anti-canonical divisor, a certain K3 fibration, which is chosen so that these correspondences are invertible. In other words, we choose a particular X such that once you know the Gromov-Witten theory of X and all these Noether-Lefschetz numbers, you can recover these guys. Okay? Because these are really what I'm interested in. I'm interested in the Gromov-Witten theory of K3 surfaces, but I'm going to choose global X's to which I can apply the MNOP conjecture, for which I can recover the invariance of S from all these invariants and all these numbers. All right? So such a thing exists. And then I'm going to apply the MNOP conjecture. So this is sort of the last step of this. The MNOP conjecture says, suitably modified, the Gromov-Witten theory, exponentiated to make it a disconnected theory, I'm counting disconnected curves, is the stable pair theory after this change of variables. Okay, so you're not supposed to understand that. There's an analytic continuation going on. But all that matters is it says the content of this theory is the same information, it's the same data as the content of this theory. Okay? If you count curves one way or the other, you have the same set of numbers. In terms of individual numbers, it's impossible to deduce anything. But the contents of the both theories are the same. And that's been proved by Pandharipande-Pixton for projective Calabi-Yau threefolds, which can be degenerated to unions of toric varieties. So in particular, it's proved for the X that I chose. Okay? So for the X I chose, I can relate the Gromov-Witten invariants to the stable pair invariants, and via these Noether-Lefschetz correspondences, I can relate both of those to the Gromov-Witten invariants of the K3 and the stable pair invariants of the K3. And because I chose X to have invertible correspondences, I can actually get an MNOP conjecture for the invariants of S. All right? So the upshot of all this is that the MNOP conjecture actually holds for this sort of local twistor threefold. The invariants of S, stable pairs or Gromov-Witten, are the same. All right, sorry. So I'm running out of time, so I just go through this very briefly. So what was the plan of proof? We used the MNOP conjecture plus degeneration to get this local MNOP conjecture. So we've reduced everything to computing stable pair invariants on a twistor threefold. And then by that degeneration and to the normal cone and so forth, and further localization and so forth, we end up with just computing stable pairs on this trivial geometry, S times C. All right? Really, it's the rubber, but we do some further arguments, and you get down to S times C. And then there was just one last argument I wanted to explain, which is that stable pair theory has this advantage that it has a so-called symmetric obstruction theory. So vector fields on this moduli space are dual to obstructions. Okay? So in particular, we've already used this. There's one vector field which is translate in the C direction. Okay, so this vector field. And that was what was dual to the trivial piece of the obstruction theory that we removed to get to the reduced obstruction theory. But we're going to use it on another vector field, and it's a bit strange, but this is what it is. You imagine a stable pair on S times C, supported on the central fiber, but that's sticking out. It's scheme theoretically sticking out. And what I do is I break off the last piece. So if it sticks out sort of 3 units, I leave 2 units alone, and I break off the last piece. So this all makes sense in some scheme theoretic language. Okay, so imagine such a thing. I can define such a thing. And differentiating it at t equals 0 gives you a new vector field, not on this whole space, but on the C star fixed space. So it gives you a vector field in this direction. It's not a vector field tangent to this. It's a sort of a normal vector field from this into this. Okay, so by the geometry of stable pairs, just the way you can split them up and move them. So I'm just translating in the C direction again, but I'm not translating the whole thing, just the sort of the last piece of a scheme theoretic thickening. When you do that, you get a new vector field and therefore a new obstruction. And the vanishing result is the following. This vector field shows you the following. It shows that almost every component of these C star fixed stable pairs do not contribute. The only ones which contribute are the ones which are uniformly thickened, so the ones that look like this. So these are sort of curves which have been thickened in the C direction, and with points on them which have been thickened in the C direction uniformly. So those can contribute. But these cannot, because the curves are not uniformly thickened. This one's been thickened less than this one, and these points have been thickened less than these, and so forth. Okay? So only these contribute. And the reason is that this vector field here turns out to be the same, I lost it, as the original vector field that I've already used for these guys. So here, there's no additional vector field. There's a vector field, but it's proportional to one I've already used. So there's no additional obstructions. Over here, it's a vector field which looks different here to what it looks like over here. So it's proportional to the old vector field here with proportionality constant, which is different to the constant over here. So it's not globally proportional. So it gives me a new obstruction, and that new obstruction gives me a new vanishing on the moduli space. All right, sorry, I rushed over that. But basically, these don't contribute, and these do. And these guys are really simple. The moduli space of these, well, they're just thickened from a stable pair on S. So the moduli space of these are just the moduli space of stable pairs back on S. So this is just a multiple cover formula. It's saying the only thickened guys which contribute in the three-dimensional geometry are the guys which actually lie more or less on the central fiber, or they lie on the central fiber and then they're multiply covered in a completely trivial way, which we can compute. So only trivial multiple covers contribute, and so we can really compute. So we're finally left with a calculation just on S, and then I was going to tell you, but I won't because I've run out of time, how you do that calculation on S. But work of Martin Kuhl and I, using very classical geometry, incidence varieties, and so forth, did those calculations some years ago in relation to a virtual version of the Gopakumar-Vara conjecture. And that turns out to be very simple, but that's older work. And so you do those calculations, and what you find is they depend only, if anyone knows the Gopakumar-Vara conjecture, they depend only on topological quantities. So where do we end up? So the result is, the calculations that Martin Kuhl and I did, the answer depends only on topological quantities. It only depends on the square of beta, and n, of course, not the divisibility of beta. And that's what gives the KKV conjecture. That's what shows that the BPS numbers don't depend on the divisibility of this class beta. So you can calculate in the privative case, which was a calculation done long ago by Kawai and Yoshioka, and it gives you the KKV formula. Okay, sorry to run over.